Let's very quickly review exergonic and endergonic reactions. Remember, an exergonic reaction is one which releases energy, and an endergonic reaction is one that requires an input of energy. When we were discussing exergonic reactions in an earlier video, we were looking at this particular graph here, and we talked about how, in this case, you're starting with reactants that have high free energy, and you end up with products with low free energy. When you make this change from the reactants to the products, based on what we know regarding the first law of thermodynamics, that we can't create energy, we can't destroy it, when you go from reactants that have high energy to products that have low energy, that difference in energy, or that delta G, has to go somewhere. And in this particular figure, we're just showing that energy released as a glowing orb. It's now time for us to fill in, well, what actually happens to that energy? Typically, cells will use this released energy to perform cellular work. So let's fast forward a couple slides here and talk about cellular work. There are three main kinds of cellular work that cells do. They can do chemical work. This includes driving chemical reactions that are endergonic or require an input of energy. Number two, cells do transport work, so they have to transport materials across the membrane. Think about the things you learned about active transport in chapter 7. And then also mechanical work, movement of motor proteins, movement in terms of muscle contraction. Cells do that kind of work as well. And so we have to now understand, well, these are all things that oftentimes require an input of energy, right? Chemical reactions, transporting something, or doing mechanical work. How does a cell pay for these kinds of work? Cells will typically manage their energy resources by performing something that's called energy coupling. So they will take two processes. One process is endergonic. They need to pay for this process, right? Needs an input of energy. And they will link it to an exergonic process, one that releases energy. And this makes a lot of sense, right? If you take one process that releases energy, you can take that energy and then funnel it in to the process that requires an input of energy or is endergonic. You're coupling the two reactions together, hence why we're calling it energy coupling. Now, most energy coupling in cells is mediated by the molecule ATP. Recall, ATP stands for adenosine triphosphate. Let's review this molecule. I know we talked about it earlier, but we kind of talked about it a little bit more broadly or generically. I want to talk a little bit more about the details of this molecule and why it's so important in cells. So adenosine triphosphate, ATP, here is the full structure of this molecule. And really what ATP is an RNA nucleotide with 3 phosphates attached in a tail. So you've got your adenine, hence why we call it adenosine triphosphate. Here's your adenine nitrogenous base, and that's linked to a pentose sugar. This is an RNA nucleotide, so this is ribose. And then attached to the sugar is your triphosphate tail, 3 phosphates in a row. Now, this is an energy-rich molecule. It has a lot of potential energy, or more specifically, a lot of chemical energy based on its structure. Why is this? Why does ATP have the ability to store a lot of energy? Well, if you take a look at that triphosphate tail, it's got a negative charge here, negative charge, negative charge, negative charge. That's a lot of negative charges packed into a really small space. Remember that like charges don't like to be together. They want to spread out, right, as much as possible. And so there is a lot of instability in this triphosphate tail of the ATP. Now think back to what we learned earlier in this chapter regarding stability and the amount of free energy in a system. When things have really low stability, their free energy is going to be really high. So ATP, having a really unstable triphosphate tail, allows that structure to store a lot of that potential energy. And so ATP, this energy-rich molecule, stores energy for the cell that can then be tapped to perform cellular work. How does this happen? Well, when you break the ATP molecule, and when we do this is shown down here, this is called ATP hydrolysis. It's a hydrolysis reaction. We're going to use water. We're going to break the water. And we're going to use that also to break then the ATP. When we break it, where we break it is right here in between these two phosphates in the triphosphate tail. So we literally cut off that last phosphate. It becomes an inorganic phosphate because it's no longer attached to a carbon skeleton. And what's left here is ADP, or adenosine diphosphate. And this is an exergonic reaction, which releases energy. Why is it an exergonic reaction? Well, let's think about this. If you were to cut right here, right, you are removing two of those negative charges from this tail. What you're doing is you are increasing its stability, and therefore you're decreasing its energy. And that energy, again, has to go somewhere. You can't create it, can't destroy it. And so it's released from the chemical reaction. Right, so a couple of points to reiterate here that are really important. Energy is released when the terminal phosphate bond is broken. So this phosphate bond here. And this release of energy comes from the chemical change to a state of lower free energy and not from the phosphate bonds themselves. So there's nothing special of these covalent bonds that hold the triphosphate tail together. The energy release really comes from this increase in stability of the molecule. All right, so we've still got this glowing orb that is this energy that gets released. Let's talk about how this glowing orb is then used to drive cellular work. Now remember, there are three types of cellular work that can be powered by the hydrolysis of ATP. You can use it to drive chemical work, you can use it to drive transport work, and you can use it to drive mechanical work. So what we're going to do is we're going to talk about how ATP hydrolysis drives all three kinds of cellular work. First, we're going to cover chemical work. This is probably the trickiest out of all of them, so we'll spend some time here. Feel free to pause in the video and we'll work through the figure as we go through it if you need to, or rewind if you have to. So when you take ATP hydrolysis, an exergonic process, and you link it to drive an endergonic reaction, overall the coupled reactions have to be exergonic. We're going to come back to this point in a minute, but what this means is the exergonic process has to release enough energy to pay for the endergonic process plus a little extra, right? A little extra to essentially pay an entropy tax. Right, so think about it. You go to the store and you see something that costs exactly $10, right? And you go to the cash register and you're going to pay for this item, as long as it's not a food item, which is not taxed, right? If it's a taxable item, they're going to ring you up for, $10.85. If you have that $10 bill, you can't purchase that item because you don't have enough money to pay for that tax. The same thing goes for these coupled reactions. The exergonic reaction has to have enough energy released to pay for the endergonic process plus entropy tax. Some of that energy has to be lost as heat to increase the entropy of our universe for the whole coupled set of reactions to actually take place. And again, we'll review this with an example. So let's talk then about how ATP drives chemical work. Physically, how does this happen? So ATP drives endergonic reactions through a process that's called phosphorylation. Phosphorylation literally means transferring a phosphate group, that phosphorus atom with the oxygens, right? We talked about the phosphate group earlier, taking that phosphate group from one molecule and transferring it to another molecule. Typically, it gets transferred to one of the reactants of the endergonic reaction. So now this reactant has this extra phosphate group attached to it. It's a little bit more complex. It has slightly higher free energy, and it is called a phosphorylated intermediate. It's called an intermediate because it's not a reactant anymore. It was changed. It's not a product because we're not done with the chemical reaction. So it's somewhere in between. It's an intermediate, and it has a phosphate group attached to it, so it's phosphorylated. Okay, so let's look at an example. This seems like a really complicated slide, but it's divided up into 3 sections. So let's take a look at the first section. This first section explains the chemical reaction that we want to take place in a cell. This is an endergonic process. The reason why I can tell it's an endergonic process is because here it gives you the delta G, the change in free energy, and the delta G is positive, a positive 3.4 kilocalories per mole. A positive delta G means this process is not spontaneous and requires an input of energy. And so this chemical reaction, what do we want to accomplish? We want to make the amino acid glutamine. And we can do this by taking two smaller molecules, glutamic acid and ammonia, and link them together. We're going from simple lower energy molecules to building a more complex higher energy molecule. It also makes sense that this would be an endergonic process requiring an input of energy. So let's say the cell wants to do this. So it's got to pay for it, right? The way it can pay for it is by using a molecule of ATP, right? So in the middle, we've got now our coupled reactions. We are looking at the hydrolysis or the breaking of an ATP to release energy to link together the glutamic acid and ammonia to make the glutamine. So let's walk through it. All right, so we're starting with the glutamic acid, which is one of the reactants of the endergonic reaction, and ATP. We're going to break the ATP, hydrolyze it. So that means we're going to take off that last phosphate from the ATP and we're going to give it to the glutamic acid. And so now here we have the glutamic acid with a phosphate group added to it. This is our phosphorylated intermediate. This is the way the ATP transfers its energy, right, to the endergonic process by literally physically taking the phosphate group off of the ATP and attaching it to the reactant. All right, so this phosphorylated intermediate now has a little bit higher energy. It's a little bit more complex, a little bit more unstable, therefore has more energy. It has enough energy now to react with the ammonia. So the ammonia is going to come in. It's going to take the place of that phosphate group there. The phosphate group is going to just float off, leave as an inorganic phosphate. The glutamic acid gets linked with the ammonia, and then here's what's left of the ATP after the phosphate group was originally removed back here, and that's your ADP. So now you have successfully used the hydrolysis of ATP and the energy that was released there to make your glutamine. Down here is the energy accounting. Let's see if this makes sense. So what this is telling us is if we want to link the glutamic acid and the ammonia together, this is an endergonic process to make the glutamine, and it requires 3.4 kilocalories per mole. So we got to pay for that. Okay, so we're going to use an ATP molecule. This is an exergonic process when you hydrolyze it. So when you cut ATP to form ADP and the inorganic phosphate, this will release 7.3 kilocalories per mole, right? This is a negative delta G. This is a spontaneous process. It releases energy. So if we add these two together, right, we release 7.3 kilocalories per mole, and we need 3.4 kilocalories per mole. Overall, for the coupled reactions, that gives us a net delta G of negative 3.9 kilocalories per mole. That means those extra 3.9 kilocalories get released. So overall, with that negative delta G, these coupled reactions are exergonic. There is enough energy here released from ATP hydrolysis to pay for making the glutamine, plus extra to pay for that entropy tax. All right, so when we're talking, I'm going backwards now, talking here that the overall coupled reactions during energy coupling have to be exergonic, we can see that here, that we have that extra energy that's released, left over, making the coupled process exergonic.